Welcome to another fabulous day in Calculus 3. Let's finish up the directional derivatives and gradients lecture. Last time we looked at what a directional derivative was, and it's basically a scalar, and it's a slope, and it involves the dot product with the gradient. And the gradient is kind of cool. It's a vector that contains the partials of a function. So let's look at some properties of the gradient with this theorem, shall we? So let f be a function of two variables, say x and y, and it's differentiable at a point xy. Then del f, that's the gradient notation, del f, if del f equals the zero vector, then the directional derivative at any point would be equal to zero for all unit vectors u. That d u is the directional derivative notation. We looked at that last time, and this right here is a gradient. Okay, so that's the first part of the theorem. Number two, the direction of maximum increase, that's like maximum slope, also known as steepest ascent, is given by blank. That direction is actually given by the gradient. Fill in the blank. The maximum value of this increase. So the gradient gives you the direction, but what about the actual value of that maximum slope, if you will? It is the magnitude of the gradient at that point. So the direction of minimum increase or steepest descent, that's if you were a hot dog skier and you want to go down the downhill, the steepest, just go the opposite direction of the gradient. So negative del f, opposite direction of the gradient. And the minimum value of this decrease would be the negative, the magnitude of the gradient, negative of the magnitude. Okay, I'm going to prove this theorem on the next page. So let's do part one first. Part one's easy to prove. So part one basically says, hey, if your del f, your gradient, is the zero vector, then things aren't just, they're not very interesting. Your directional derivative will be zero and it's not that fun. So if del f xy equals the zero vector, and I'm putting a little vector notation on top of the number zero so it doesn't look like the scalar zero, then for any direction u, where u is a unit vector, we have the big D, that's the notation for directional derivative, in the direction of u, fxy, which we all know from last time is simply the dot product of the gradient with the direction vector u, will be the dot product of the zero vector with the little cos theta, sine theta direction vector, and that's clearly going to be zero. Okay, and so I'm done with the first property there. That one was easy to prove. Now, what if del f isn't the zero vector? Well, then things get a little bit interesting. Then how about we let theta be the angle, I'm writing all this down, between your del f, your gradient, and the unit vector u. Now, you remember when you have two vectors and you're trying to calculate the angle between them? I'll just make a little picture. Like, let's say your unit vector was pointing that way. Okay. And let's say your del f was pointing way over here. So it's just say, fine. And then we want to talk about theta, the angle between them. I hope you remember from like the first week of class that the dot product of two vectors is the same as cosine of the angle between them multiplied by the product of their magnitudes. Okay, so that's got to be the case. Now, when is this quantity on the right-hand side the max? So we want to maximize this. Well, we know that the magnitudes are always positive numbers. That's got to be true. So the only big thing that's going to really affect it is cosine, and cosine can go back and forth between a +1 and a -1. So if we want to maximize that product, we want to see when is cosine at its max. Yeah? Anybody know when cosine is maximum? So the max of this directional derivative will be when cosine theta is at its max, which is a 1. That's the highest cosine can get. And what is the angle when cosine is a 1? So cosine theta equals 1 means theta is equal to what? Anybody know?
0 degrees.
Yeah, 0. So what does that mean? Look at my little picture here of the direction vector u and the gradient. So if we want to maximize that directional derivative, we want that theta to go to 0. In other words, we want the gradient and the unit vector to be pointing in the same direction. So the max slope, if you will, obtained when u points in the same direction as the gradient. And that's the big takeaway from that theorem. Same direction as del f. Because del f is pointing you in the steepest descent. Yeah. Now the minimum is obtained when cosine theta is at its minimum. So if you're going to keep going here, the minimum occurs when cos theta is at its minimum, which is -1. And that means theta is pi, or 180 degrees. So if you want to get your minimum slope, just go in the exact opposite direction of your gradient. Negative del f is the direction for steepest descent. Okay, and I'm done with your slope. So let's reiterate here. To visualize the properties of the gradient, imagine a skier on the coming down a mountain. That z equals fxy gives the surface there, and it gives the altitude of the skier. Then the vector negative del f indicates the compass direction of the steepest descent. Let's do another kind of application. One of the great applications that we've been covering is always treating z equals fxy as altitude, a surface in 3D. There's another way to think of a function of two variables also, instead of altitude. You can think of it as temperature. So Txy gives a temperature corresponding to some point xy. It's a great application. So if you had a hot plate here, here's a hot plate, and we'll overlay an x and y coordinate system on top of the hot plate. If you plug in some point here from your hot plate, like just say 0, 0, you'll get the temperature of the hot plate at that point. So if you plugged in, say 0, 0 into this temperature function, it looks like the temp would be 20, and they're talking about degrees Celsius, so 20 degrees Celsius. And you can plug in any other point from your hot plate there, and it'll correspond to a temp instead of an altitude. Fine. So imagine an ant is walking on the metal plate. And let's say the ant is located at 2, -3. So here on my hot plate, down here at the point 2, -3, there's my ant. And let's say this was a heat-seeking ant. I don't think there is such a thing, but if he was a heat-seeking ant, let's say the ant would like to get warmer. What direction should he move so that his temperature would increase most rapidly? Well, the answer is he should move in the direction of the gradient, del t. And that direction, the vector, is given by a vector with the partials as the components. So let's first find the gradient, and then we'll evaluate it at the point where the ant is located. So if you look at this temperature function, the partial of t with respect to x, -8x, and the partial of t with respect to y, -2y. And if you evaluate t at this point with x and y coordinates 2, -3, respectively, I get the vector negative 16, 6. Now, if you graph negative 16, 6 in standard position, how would you do that? Well, you'd go way over here, find negative 16 on the x, 16 or 6 on the y, graph the point negative 16, 6. Let's just say it's way out here. I'm not drawing the scale, obviously. And then here's the standard position gradient, but you need to translate that vector so that it's sticking out of the point where the ant is located. So you need to move that vector so that he's still going to be the same direction and still the same magnitude. It's going to look like that. So the ant needs to move that away if he wants to warm up. Okay. Now, letter B, if the ant does move in that direction, what is the rate of the ant's maximum increase? So the answer to letter B is the magnitude of the gradient at the point 2, negative 3. Oh boy. So the magnitude would be the square root of the sum of the squares of the components, and I get, square root of 256 plus 36. I get 292 square root of, which is approximately 17.09. And this is a slope, so it's degrees Celsius per centimeter for this ant. So if the ant moves in the direction of this vector, he'll start increasing at that rate. That's pretty much, wow, 17.09 degrees per centimeter. That's heating up a lot. Now, I want to address this, but I want to say there is a little bit of a caveat here. The instant the ant moves in this direction, even a little bit, the moment he moves, he's on a new point. And so the direction will change again. So let's say he moved a little bit, then the gradient is going to change again. And so it's going to point him in a new direction. So I claim it's going to maybe point him that way. And then if he moves a little bit more, it's going to point him that way. So it's going to keep changing as he moves. So he'll eventually end up at the hottest point on the hot plate. So where is the hottest point on this hot plate? Well, just the way the temperature function is, I hope you can see here we have a number minus a positive number minus a positive. So the maximum temp will be located at the point 0, 0 for this particular hot plate, because it's got that particular function. So the ant is going to keep, first he'll start off going in the gradient, and then the gradient will change, and then it'll change. And his path is going to take him basically to the hottest point there at the on the hot plate, and then the gradient will be the 0 vector. So then he better not move. Okay. Now, what are the level curves for this function? So you remember level curves can be found by setting your function equal to a constant, say c. So 20 minus 4x squared minus y squared equals some constant. So if you rearrange this equation so you can kind of get a better handle on what the graph would look like, this is going to graph a bunch of ellipses. So those are the level curves for this particular function. So what does that mean? Like if you let c equal some number, your favorite number, I don't know, let it be, I'm just going to make something up. Say c was 16. Then on the left-hand side, 20 minus 16 is 4. 4 is equal to 4x squared plus y squared. If you divide both sides by 4, so you could get the standard equation of an ellipse, you'll have x squared plus y squared over 4 equals 1. That's an ellipse centered at the origin. With -1 and +1 as the x-intercepts. And -2 and +2 is the y-intercept. So here we have that. So that's one of the level curves. What do you think the level curve is right here at the point 2, -3? Well, if you take this level curve and you let x equal 2, y equal -3, you'll find out what c would have to be for that level curve that the ant is located on, okay? So I'm just going to solve it for C. Let's see what happens here. 4 times 4. Da, 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 da. Okay, so 20 minus C equals 25. If I add C to both sides and subtract 25 from both sides, I get C is negative 5. Okay, and that will give you an ellipse. What kind of ellipse? Well, you know, you could graph it. So I'm just going to sort of eyeball it. It's going to give you an ellipse looking something like that. Okay. Why am I going through all this trouble? I'm going somewhere, trust me. What I want you to notice is that vector that we first did, the negative 16, 6, I'll just redraw it here like that. I hope you can see that it's orthogonal to the level curve that the ant is on. Now, I want to talk a little bit also about this level curve. If this ant wants to stay at the same temperature or a level temperature, he'll stay on this ellipse that he's already on, and then he won't change in temperature, because the claim here is that if you stay on this level curve ellipse, your temperature won't change. All the points on that particular ellipse share the same temperature. So if the ant were interested in staying the same temp, he would continue to walk on that ellipse. I don't know any ants that walk in an elliptical fashion, but anyway. So what are we saying? From this example, notice that the gradient is, and so you're going to fill in this blank in your course reader, orthogonal to the level curves. In other words, the rate of change of temperature in the direction of a unit tangent vector. So if you were doing a tangent vector to your level curve, you wouldn't change your temperature. You would be 0. So what we can say is that the dot product of our gradient with some tangent vector, say u, would be 0, because you wouldn't be changing at all. And that's going to lead us to the next theorem. Big theorem here. Put a star by it. A gradient is normal. Normal means orthogonal, okay? Well, why don't they just say orthogonal? They use normal kind of loosely a lot of times. It's orthogonal. So here it is. If f is differentiable at some point and the gradient is not the 0 vector, then you're guaranteed your gradient is normal to the level curve. Cool. Now let's jack it up some. What if you had a function of 3 variables, which I told you you can't graph because you would need 4 dimensions? Okay. But we can still talk about gradients and all that. We still can. Yeah. Suppose you have a function of 3 variables. And we can kind of use the temperature model. This function fxyz could represent the temperature in 3D. So let's say you pick a point in your room, you know, x, y, z coordinates, and then plug it into this temperature function, you get the temperature in your room. So every point x, y, z in your room would correspond to some temperature here. You could. That would be a great model for it. Let's find the gradient of this function f at a particular point. Now the gradient is going to be a vector, and it's going to be a vector that contains the partials. In this case, it's got 3 partials because we have 3 independent variables. So the gradient at any point x, y, z for this guy is going to be the vector with 2x, 2y, and negative 4 as components. Fine. Now, if you want to find the gradient at the point 2, 1, negative 1, just do some substitutions. I get 4, 2, negative 4. So what's the meaning of that? Well, if you were a fly flying around your room and you were located at the point 2, 1, negative 1, and if this function did represent temperature, and let's say the fly wanted to get warmer, if the fly would go in this direction, in the direction of the gradient, then the fly would increase his temperature. That's all. Cool. Let's find a directional derivative of f at the point 2, 1, negative 1 in this direction, v. Now, remember, when you're doing directional derivatives, the all-important thing, I want to make sure you get this because this is going to be on your midterm. It's going to be on the final. And yes, I'm going to try to trick you. I'm going to try to trick you, people. Hang on. Let me get over, where was it? I think I passed it. The directional derivative. Where is it? Somewhere here. Here it is. My favorite, the alternative version with the dot product. This u here, when you take your dot product with your gradient, that direction vector has to be unitized. Key, know this for the midterm, know it for the final, because if you don't, no partial credit. You want to maximize your points? Unitize it, baby. Okay. So in the example we're about to do, and we're about to find a directional derivative here for a function of 3 variables, we need to unitize this direction vector that they want us to find the slope in. So unitize, here we go. I'm going to first get the magnitude of v, square root of 6 squared plus 3 squared plus 2 squared. Oh my goodness, what is 36 plus 9 plus 4? Ooh, wow, it's 49, nice. So square root of 49 is 7, great. So then my unit vector will be the vector with -6, 3, -2 divided by 7, and that's going to be -6 sevenths, 3 sevenths, -2 sevenths. Yay. So now my directional derivative for the function at the point 2, 1, -1 is going to be the dot product of the gradient at that point with this unit vector pointing in the direction that I want to find the slope, if you will, or the rate of change. So, you know, let's do all the arithmetic here. Oh, yucky. -24 sevenths plus 6 sevenths plus 8 sevenths. Woo. -10 sevenths. That's a slope. Directional derivative, remember, is a scalar. So you better not give an answer that's a vector. So answer, there it is, -10 sevenths. What does that mean? That means if I were a fly and I were flying in the room and I flew in the direction of this vector here, my temperature would actually decrease -10 sevenths per, I don't know if we're doing it per centimeter or whatever. Interesting. So if I wanted to get cooler, I would go in that direction. Now, what's the direction of maximum increase? So let's say I'm a fly at that same location and I want to get as warm as possible, as quickly as possible. Then the direction is going to be in the direction of the gradient. So, and we already got it. So the answer is this vector. That's the direction that the fly needs to take if the fly wants to increase his temperature the fastest and the most. Now, what is that maximum rate of change that the fly's temperature is going to change? That will be the magnitude. Oops, I keep doing that. That's a 1. The magnitude of the gradient at that point. So we're going to go the square root of 4 squared plus 2 squared plus 4 squared. That's a square. What am I doing? What the heck is the square root of 16 plus 4 plus 16? Ooh, square root of 36. Nice. So 6. That's the answer to letter D. And finally, what are the level surfaces for this function? Not level curves, level surfaces, because it's a function of 3 variables. So, you know, step 1 to find level surfaces, set the function equal to a constant. So x squared plus y squared minus 4z equals some constant. And if you look in that section way back when we were discussing quadric surfaces, when one of your variables is not getting squared and the other 2 are, you'll have paraboloids. What's a paraboloid? You know, it kind of looks like a 3D version of a parabola. It's an analog. It would look something like this. There's a paraboloid. Cute. And we're done with that problem. Now, what about the gradients, del F and del big F? Those are 2 different animals because del F is a 2D vector and del big F is a 3D vector. And this is going to come up a lot in the next section. So I'm going to plant a seed right now. And you may not totally understand what I'm saying right now, but just try to go with it. And then it'll become crystal clear when we get to the next section. So here's what's weird. When you do the function of 2 variables, So like z is equal to f x comma y. You can graph it, and the graph is like a surface, like something like that, say. When you find the gradient of it, the gradient is a 2D vector. So it's as if you're standing here with your skis, but you have like a flat little compass. Have you guys seen a little compass, you know, with like, you know, compass with a little arrow pointing? You have on your palm a flat compass pointing you in which direction to go if you want to maximize your slope. So the gradient is 2D, which is weird because here you are on a 3D surface, but you need a 2D vector to point you in the direction that you need to go if you want to maximize your slope. That's interesting. And this is just repeating that your gradient del F will always be normal to your level curve. So if your level curves just happen to look like sine curve, then your gradient at any point would be orthogonal, you know, as you go. So that's kind of cool. And we're going to extend that to the level surfaces with big del F. So this gradient here is a 3D gradient. And that's going to come up soon. And if you have a 3D gradient, it will be orthogonal or normal to level surfaces. Okay, this is key. All right. Woo!